matrix product operator generally looks like. Right, so again, we work on a periodic chain with L site, and we have a local tensor here, and with a two-dimensional virtual space. And we contract the virtual legs in this following way. In this way, we get an operator that acts on L legs that give you another state on the original Hilbert space. So this tensor turns out to be the following. So in formula, you can write this as trace where this U is defined as follow. Okay, so let's unpack this formula a little bit. So first of all, my convention is that 0 and 1 are the eigenbases for the poly Z operator. Plus and minus are the eigenbases for the poly X operators. This is a bra state for the J's physical leg. This is a cat state also for the J's physical leg. But let me not repeat the subscript J here again. Both of them, everything here you see in this local tensor has physical legs on the J's side. Okay, so each entry here is an operator acting on the J's qubit, but it also has legs in the virtual direction. And as I said, the virtual space is two-dimensional. So the tensor should be a 2x2 matrix in that virtual space. Okay, so here I present the matrix. Is that clear to everyone? And to obtain the final operator, you multiply this operator value matrices in this order, and you take the trace in the bound dimension. So this trace is only in this two-dimensional bound space. All right, so this is an explicit expression, and the claim is that after you do the algebra, this is precisely that operator. It takes a little bit of work to show that they are equivalent. Probably I won't do that on the blackboard, but you can check one of the references I gave yesterday for the derivation. Now this expression has a lot of advantages. So first of all, it makes the translation symmetry manifest because of this and because of the cyclic property of the trace. So that's one advantage over the one over there. It also has another feature I want to emphasize. So there, it might seem that the root 2 seems arbitrary. Of course, one way to say that we want to fix the root 2 such that d squared is 1 plus eta times t. That looks closer to the continuum algebra. But apart from that reasoning, apart from reasoning from the continuum, there's no clear reason why you would like to put the root 2. But from this expression, it's more natural that you only rescale this operator by rescaling the individual local factor. So maybe you want to rescale your u by a factor of 7. But if you do that, that will give you 7 to the lth factor for the final operator. And the intuition behind that is that in the continuum, this is an operator that supports on a line in your Euclidean spacetime. And the allow counter term you can add to such a line operator has to be extensive in the length of the line. So it's natural to rescale this by some power of L, but it's not natural to rescale it by, say, just a single factor of root 2. And somehow the MPO presentation prefers that factor of root 2, which ultimately gives you the normalization in the continuum. It's not a full justification. It's just saying that on the lattice, this nice MPO presentation gives you a preferred normalization. Okay, so those are the good thing about this presentation. But there are also some, well, maybe I shouldn't use the word disadvantages, but this expression doesn't make the fact that it's non-invertible manifest. Just by looking at this, I don't see why there has to be a kernel. Of course, if you study it a little bit longer, ultimately it's the same operator, so you will find a kernel. But it's not manifestly obvious from this presentation. And regarding that aspect is the first expression that makes the non-invertibility manifest. So both expressions are great. They have their own advantages and disadvantages. And I think by this point, we have already seen 3 presentations for this operator, 2 on the blackboard, and the third one from the fermionic presentation. The fermionic presentation make the algebra manifest. And there are actually a couple of more presentations, but I won't bother you with all the different presentations. Each one of them has its own advantage and disadvantage. Okay, so let's do some calculation using the MPO. Oh yeah, Juven. Yeah, let me sketch that a little bit. But maybe wait a little bit because that will be more naturally connected to the defect discussion. Yeah, so later on, I will sketch a derivation of the operator from the defect. I will not do it in details on the blackboard, but essentially, you can derive this from the defect. Yeah.
So this operator was map of O plus stage to the BC plus, right? But would you just have like can you change the sign map to BC minus?
I'll get to that. That's something that I will discuss, yes. The short answer is that it annihilates the GHZ minus, right? So I'll write down the full thing, full action later on. And I will also generalize the relation you have in mind to higher dimensions at the end of the lecture. Yeah, thank you. Yeah, Yunqing.
The phase, 2 pi over negative phase can be washed out every time.
That I agree. Yeah, so the phase, I will still just justify it by the algebra. I don't have a better explanation. Any other questions before we play with the MPO? Okay, so one defining property of the operator D, as if you recall the way I motivated the whole lectures, is that we want an operator that implements the Cramer's linear transformation. So we wanted to satisfy dxj equals zj plus 1 d, and dzj plus 1 equals xj plus 1d. It's not terribly difficult to show this using the first expression up there. Probably take you 5 minutes to do it, but it's actually more illuminating to do it from the MPO presentation. And that would nicely connect to Ignacio's lecture where he talked about general MPO. So maybe we can take the next 10 minutes to discuss this calculation. All right. So using this explicit expression for U, you can show the following. Okay. So I just act an xj operator, the poly x operator from the right. Okay, that's something very easy to do, right? Because x, when acting from the right, it pick up a plus sign on this broad state. It pick up a minus sign on this guy, and so on. So you just sprinkle 2 minus sign on that matrices. And graphically, you can write this in the following way. This is the U tensor that I have. And you put the x operator from below. And you can convince yourself, it's just a one-line calculation, that this equals this. So everything in this blackboard font is in the bound dimension. So this is a poly Z in the bound dimension. So that's just saying that this is 1 minus 1, 0, 0. Okay. So it's just a simple identity you can derive from the definition of U. But this means that this diagram equals this. There's some local algebra between the MPO tensor and the poly X. And similarly, you can show the following. If you have this Z in the bound space acting on uj from the left leg, so let's write it in terms of diagram, then this equals the physical poly Z acting on U. All right, so just some simple identities you can really verify in 10 seconds. Now with these two equalities, you can now verify one of the equations over there. So this is our operator D, but I'm just looking at it locally. And you're sending an operator X from this leg. Let's say this is J plus 1. Right, so using the first equality, you change it to and then you apply the second equality to turn this, to move this Z upward and this Z upward. And this precisely gives you the Hermite-Wenier transformation on the operator X. So this MPO presentation gives a very local way to realize the Hermite-Wenier transformation. You see, you don't have to worry about what's happening away from size J and size J plus 1. Everything takes action locally. Now, similarly, you can show this action. And this. And from this, you can derive that if you're sending two Z's, only one X comes out. But at this point, there's a question that we should have asked yesterday when we wrote down the Hermite-Wenier transformation. Right? So this operator D acts very nicely on X and on ZZ. But no one asked me how it acts on Z itself. Right? What is DZ? Well, the first thing is that the way we define the action of a non-invertible symmetry on some local operator is no longer by conjugation, because we no longer have the luxury of taking the inverse of the non-invertible operator. The inverse doesn't exist. So as a compromise, we define the action by pushing the operator from the right to the left and see what we get. But there's no guarantee that when you push the operator through, you can write the right-hand side as some operator times D. And what's happening here is that only for those Z2 symmetric operators, Z2 even operator, when you push it through D, you get a nice expression like this. But for an operator that carries the Z2 charge, such as ZJ, the poly ZJ itself, such an expression doesn't exist. And you can see that very explicitly from the MPO presentation. So let's just do that in real time. So you can send in a Z here. And then you get an X. But then there's no relation on the blackboard, which can tell you how to move this X to upwards. So you just have an X kind of stuck in this virtual space. If you have two Z's, like this, the first one goes here, the second one will go here. And then, only then, I can use this relation to bring it up to an X on the future physical leg. Okay? All right. I think that's probably all I want to say about the matrix product operator expression. It gives a very nice presentation for how the symmetry acts on local operators. And you can furthermore do perform the algebra for the non-invertible symmetry. One of them can be done almost immediately. That's the one where you compute d times eta. How do you compute d times eta? Eta is a product of x. So you put an x at every leg going to the past, but each one will create a pair of z according to the rule there. But then the pair annihilate. So d times eta is just d. For d squared, it takes a little bit more work, so let me not do that in real time. All right. Any question up to this point? So we spend a lot of time talking about the operator. Actually, let me just make one more comment about the operator, which should be manifest from the way we derive it in the fermionic setup. In the fermionic setup, you remember when in the first step, we introduce an extra qubit. We make the Hilbert space twice as large. And we find a unitary operator in that 2 to the L plus 1 dimensional Hilbert space. And then we do the projection. So this is to say that this operator D, you can write it in the following form. So you first add a qubit between j equals to L and j equals to 1. And then you can represent this operator with some factor of root 2 as a unitary operator on a 2 to the L plus 1 dimensional Hilbert space. And then you do a projection on the extra qubit you add to the game. And this is a rather general fact that applies to many of, if not all, the non-invertible symmetry, at least in 1 plus 1D, that by adding additional degrees of freedom, adding additional qubits, it becomes a unitary operator. And the reason that it's non-invertible is because of the final projection you perform. And this is manifest from the way we derive it from the fermionic problem. All right. All right, any question for the operator? Yes.
So there's various identities that can derive in this MPO formulation. Can you use this to show that D goes with translation? Like you had DT inverse.
Yeah, you could. Let me see if I want to do that in real time. Well, I can sketch the derivation. Yeah. So you want to relate D with D dagger, right? And So the first thing you want to do is to find the MPO for D dagger. That's easy. You just take the dagger of the matrix over there. You have to be a little bit careful about when you take the dagger. Do you only take the dagger in the physical legs or in the bound dimension? But it's one of those things. If you sit down for 3 minutes, you'll be able to sort it out. So there's an MPO tensor for D dagger. And then you can show that that tensor, let's call it, I don't know, U prime. U prime is related to U by a unitary transformation in the virtual space. There's some unitary only in the virtual space that we're related to. And then using this relation, you will see that that's the same as composing a translation. I'm not giving you all the details. Actually, I think the one I'm giving is more about the reflection. There's also a relation between D dagger and reflection. Okay, any other question?
What's the consequence of having B as does it show that the system is critical?
Right. So I'm debating if I should talk about that first, or let me talk about that first. Yeah, I was going to talk about the defect, but since you asked, so let's talk about its consequence. Okay. So instead, before I give the general statement, let's consider a simple example which will demonstrate all the properties we would like to show. So we start with the critical Ising model. Actually, let me make it non-critical. Let me add a G deformation here. So this is just the original Ising model. And as we discussed, when G is 1, it commutes with the operator D. The question is, we don't want to solve the Ising model for the 100th time. So is there any deformation of the model while preserving the symmetry of interest to us? So here's one deformation. But before I write down the deformation, let me just say it's actually very easy to find such deformation. And there are two ways to think about it. The first way is that we spent the last lecture talking about Jordan-Wigner transformation, talking about lattice bosonization. We map the problem to the fermion problem, and then we map it back. But most of the time we spent last lecture was about a global property. If you only want to check the symmetry locally, that's extremely easy. Because this D, when you go back to the fermion problem, is just a Majorana lattice translation. So anything you can write down on the Majorana side that is translationally invariant will map to something that is invariant under D. So there are infinitely many such terms you can write down if you start with the Majorana chain. You can write down some 4 Fermi interaction, etc. But even if you don't care about the fermion description, it's easy to check it directly using the Pauli operator. So here's one example. And I should say that this particular deformation was considered by O'Brien and Fendley in 17. Okay, so it's a 3-body interaction. And you can easily see that under the Kramers-Wenier transformation, X goes to ZZ, ZZ goes to X. So you just swap the 2 terms. It's manifestly invariant. So this is a deformation that preserves D. And now we can ask what the phase diagram look like. So let me also draw the phase diagram including G. But keep in mind that only along the axis you have the non-invertible symmetry D. On this 2-dimensional plane, at the generic point, you only have the Z2 symmetry. So here's 0, here's 1. So over here, when G is very large, again, we are in the disorder phase. And here we are in the order phase. So the spectrum looks like this. Right, so you have a unique ground state, and then there's an order 1 gap. And in the order phase, you have two very low-lying states whose splitting is exponentially small in the volume, and then you have an order 1 gap. This point was the critical Ising model that we started with. So we know that point is the Ising conformal field theory. Now, it's a fact that if you look at the Ising conformal field theory, there's no relevant deformation that will preserve this non-invertible symmetry D. The only the leading deformation that preserves both the Z2 and the non-invertible symmetry is quadratic in the stress energy tensor, sometimes known as the TT bar deformation, which is irrelevant. So that means this lambda deformation, which is the lattice deformation, whatever it corresponds to, must be irrelevant to leading order. So it means that there's an open window here. Where the phase stays as the Ising CFT. But then it hit a critical point where the central charge is 7/10 at this point. And that's the second minimal model. It's a tricritical Ising CFT, which from the field theory calculation, you can also show that has a non-invertible symmetry. And after that point, the model becomes gap. So on this line, the model is gap. But interestingly, it has 3 states. We have 3 low-lying states whose energy splitting is exponentially small in the volume, and there's some order 1 gap. So this is what the phase diagram looks like. And you notice that along this line, it's never a trivial gap phase. And what do I mean by a trivial gap phase? I mean a phase that is gap with an order 1 gap, but with a non-degenerate ground state. You are either in a gapless region, described by some conformal field theory, or you have a gap phase with 3 degenerate ground states. Not even 2. Somehow it's 3. For this phase diagram, it's intuitive how to understand the 3. On this side, you have a disorder phase with 1 ground state. You have an order phase with 2 ground states. And there's a second order Ising transition. That's a standard story. But when you move to here, it becomes a first order transition. And the 3 exactly comes from the 2 plus 1. Now, you might wonder if this is a more general feature of the non-invertible symmetry, or is it just an accident of this model? Any question about the phase diagram up to this point? So the claim is that for any Hamiltonian, that commutes with this non-invertible symmetry D, the low energy phase must be either gapless, such as the Ising or the tricritical Ising CFT, or its gap with number of low-lying states or superselection sectors in a multiple of 3. And you can see that both scenarios are realized by this particular deformation studied by O'Brien and Fendley. So it's a kind of constraint that smells a little bit like the Lipschitz-Matisse type constraint. It forbids, in particular, a gap phase with a non-degenerate ground state. The way one can argue the 3 is that the way that the operator D acts on the local operator is the same as gauging a Z2 global symmetry. So in the case when it's gapless, there's not much you can say. You can probably do some bootstrap and get some constraints on the scaling dimension. But in the case of when it's a gap phase, all you have to do is to go out there and see how the Z2 gauging acts on different gap phases. In 1+1D, if you have a Z2 global symmetry and the system is gap, there are not that many choices. You don't have any non-trivial SPTs for a Z2 global symmetry. Later in the lectures, we will talk about a system with Z2 times Z2 global symmetry, in which case there are non-trivial SPTs and the story is richer. But here we just have a single Z2, the eta symmetry. And there's no non-trivial SPT. And the only two gap phases you can have is either the trivial Z2 preserving phase or the symmetry breaking phase. And under the gauging, you map one to the other, just like the Cramer's one-year transformation exchanges the order phase with the disorder phase. So you learn that if you just have an order phase, that's not going to be invariant under the action of D. If you just have the disorder, that's also not going to be invariant. So the minimal scenario you can have is a superposition of the two. So this is the constraint you can derive from this non-invertible symmetry on the phase diagram in the thermodynamic limit. Why for any lambda G is, what do you?
The critical G is always 1.
So only when G is 1, the Hamiltonian commutes with the non-invertible symmetry. Otherwise, the first 2 terms fails to commute with D. Yeah. I draw the entire phase diagram just because it makes it clear why on the right region, you have a gap phase with 3 superselection sectors. It comes from the first order transition from the upper region to the lower region. But if you only care about the non-invertible symmetry, you should just focus on the horizontal axis. Yeah. I don't know. I think it was worked out in maybe not in this paper by O'Brien and Fendley, but in some other papers. For more general deformation, sometimes you can have richer phase diagrams. Sometimes there are even non-trivial Lipschitz exponents, such as the one studied by Shu-Heng and Arco and Ulmer. Yeah, so this is just a particular example.
So it's not obvious that still contains these 2 phases.
Oh, no, it might not. In fact, there are examples where the phase diagram is richer, and it's not just tricritical icing. It's even some non-relativistic gapless theory with non-trivial Lipschitz exponent. Oh, well.
The integration was different from lambda, then would there be a new D that we would get with the same property?
You mean, is there any way to, so here I assume I'm using the same D. You're asking if I can turn on some deformation that also continuously deform the operator D while preserving the same algebra? I don't know. I don't think that's possible, just because you still want the operator to act on the local operator X and ZZ in the same way. It's related to a question asked last time, that whether or not there's a unique such operator that implements the job. I suspect it is unique, but I don't have a proof. And for the same reason, I don't think you can continuously deform this symmetry operator. The intuition behind is just that everything is very discrete. And it's hard to continuously deform such a discrete symmetry. But I don't have a rigorous argument. Yes?
Is there any reason why you don't get, say, tetracritical icing safety along?
Tetracritical icing. I think, yeah, I forgot. Does the CFT also have the non-invertible symmetry? Okay. Well, I don't think there's any particular reason. I think maybe if you turn on sufficiently many deformation with some fine tuning, maybe it can be realized. I don't have a reason against that. It's just that this is just a particular example. And later on, I will say what's nice about this example. Yeah.
Why don't it be at least 3 sectors? But like, why do you have to
Oh, right. So 3, as you can see, is the simplest scenario. But as I said, the non-invertible symmetry can, well, first of all, kinematically, if you have 2 copies of order and disorder coexistent, that obviously is also consistent with the non-invertible symmetry. And pragmatically, what can happen is that because of the mixing with the lattice translation, the lattice translation can flow to a non-trivial internal symmetry in the low energy. And when that is spontaneously broken, you might get even more degeneracy. And in part of the phase diagram, with another deformation, you will see such larger degeneracy. Not in this paper, but for a different deformation. Yeah.
By imposing D, are we also imposing theta?
Good. Yes, yes. So the intuitive reason to say that, but this is not super rigorous, it's just that D squared contains eta. So this is another interesting point about this non-invertible symmetry. It's not something that can exist independent of the Z2 symmetry. It's something that its very existence depends on the Z2 symmetries. So you cannot break the Z2 symmetry without destroying the non-invertible symmetry. But you can do the other way around. You can break the non-invertible symmetry while preserving the Z2. There's no problem with that. So there's kind of a hierarchy between D and eta. And that has very interesting consequences when you apply non-invertible symmetry for some other physical contexts, such as in quantum field theory.
Translation?
That's right. Yeah. Yeah.
At a tricontrol point, if there are more general symmetry?
Yes, there are. But they are, as far as I know, they are not realized on the lattice. For instance, there's a Fibonacci symmetry, which I don't think is realized in this simple lattice system. Yeah. I don't think it necessarily have to be the case. Again, this is just a simple model that that those people did a numerical DMRG to show that this is the phase diagram. This is not something super universal. You can turn on a different deformation, and then the phase diagram will look different. Yeah. Okay. So many of the questions were about why I chose this model. Right? What's nice about this particular deformation? So there's something very nice about this deformation that will connect to many discussions. So let me tell you about that. I should say that there's a rigorous result by Michael Levine in 2019, where he showed that every Hamiltonian that is invariant under this Kramers-Wenier transformation cannot be trivially gap. So he provided a mathematically rigorous argument for that result. But using gauging, you can further argue that when it's gap, the number of super selection has to be a multiple of 3. But I will...
So if you break the boundary condition, the ground states generously will also change.
That's right. But you see, the one reason I don't want to talk about, when you say boundary condition, you can mean 2 different things, right? So you can first mean you put a system on an open chain, right? So someone could have asked me in the last lecture that why did I start with the periodic chain? Now, the periodic chain is a simple setup where I don't have to say what I impose on the boundary. The moment you have a boundary, you have to say what kind of boundary condition you choose. That's one reason. The second reason is because if I work on an open chain, I don't even have the Kramers-Wenier transformation that will leave the Hamiltonian invariant. The reason is because if you do the Kramers-Wenier transformation twice, it corresponds to a lattice translation. But on an open chain, the lattice translation is broken. Right? You cannot move all the way to the right. So the short story is that any open boundary condition will necessarily, any simple open boundary condition will necessarily break the non-invertible symmetry. So to talk about the symmetry, I'm forced to work on a closed periodic chain.
Yeah, you just said a lot of times the phase diagram doesn't depend, but here's not the case.
Here, whether or not it's whether it's gapless or gap shouldn't depend on the boundary condition, but of course the number of states would depend on the boundary condition. Yeah, and here the statement is regarding the periodic closed boundary condition. Okay. So one particular nice thing about this model is that let's take G and lambda both to be 1. Now you can show that this Hamiltonian take this simple form. It's intuitively clear. You see the ZZX term just comes from the product here, and the cross terms are the original Ising terms. The nice thing about this expression is that each local term here is a projection operator. And each one of them is semi-positive definite. So, and in fact, you can show that this is a frustration-free model, meaning that the ground state of this model will satisfy every individual term. And what are the ground states? If I write it this way, it's clear what are the ground states. I just have to set all the local terms to be 0. And what are the possible ways to set the local terms to be 0? Well, one way is that I set the 1 minus x to be 0. So obviously, the O plus product state is an exact ground state of this Hamiltonian in finite volume. Another way is to set the 1 minus ZZ to be 0 for every J. And that will lead to two other ground states. So by writing the Hamiltonian at this special value of lambda, so it's just 1 point on this phase diagram, it becomes a frustration-free Hamiltonian. Where the exact ground state in finite volume becomes manifest. And let me emphasize that these 3 states for this particular Hamiltonian are exact ground states even in finite volume. They're exactly degenerate. For each one of them, Hamiltonian vanishes. Well, forget about the constant. The Hamiltonian vanishes on these 3 states. If you go away from this point, generally the 3 states are not exactly degenerate. There are some energy splitting that's exponentially small. But at this special point, it's exactly degenerate in finite volume. I think you are right. Thank you. Did I get this part? I think I also have to make it +1. Yeah, thank you. Okay. So usually when we talk about the Ising model, right, this product state is only the exact ground state when you take the coupling G to +infinity. For any finite G, it's some states that's related to this product state by some finite depth local unitary, but it's not exactly that. And similarly, this pair of states, they are not the exact ground states when G goes to, when G is small, but not literally 0. When G is literally 0, these are the exact ground state. What's nice about this frustration-free model is that it realizes these 3 product states as the exact ground state at finite volume. So you at least see there are 3 states. Now, it takes a little bit more work to show that these are the only 3 ground states. But anyway, that was shown in that paper. So this gives a very explicit way to see where the 3 comes from for this particular model. And now we can discuss how the operator D acts on this ground state. If you have D and you act on plus plus, this will give you, just make sure I get all the factors straight. So you should think about this 2 as coming from the older phase, and this comes from the disorder phase. And having a non-invertible symmetries means that the disorder and order coexist. So when D acts on this state, it gives you 0, 0 plus 1, 1, 1, which, as was already commented, is root 2 times the GHZ plus state. If you act D on 0, 0, it's the same as D acting on the 1, 1. And that gives you back the plus plus. So the structure here is that the invertible Z2 symmetry exchanges the O spin up and the O spin down state. That's just the ordinary spontaneous symmetry breaking of a Z2 symmetry. In finite volume, the GHZ state, or any a state that's related to it by a finite depth local unitary, is the true finite volume ground state. In infinite volume, those two low-lying states split into these two superselection sectors. Each one of them is a product state, no long-range entanglement, and the two superselection sectors are exchanged by the Z2 symmetry. If you take this model, you have another symmetry D that comes into play, which will exchange all three of them. So you can interpret the low energy phase of this model, and more generally, the entire gap region along the horizontal axis as a spontaneous symmetry breaking phase of not only the Z2 symmetry, but also the non-invertible symmetry. But this is one point where it is crucial to recognize that this symmetry D is a non-invertible symmetry rather than just an ordinary Z2 symmetry. We're all very tempted to say that D is a Z2 symmetry in the Z2 symmetric sector. But if you only have ordinary Z2 symmetry, that doesn't force you to have three states in finite volume. Here it's because of the non-invertible nature, this whole algebra, this whole generalized symmetry tells you that when it's spontaneously broken, the number of superselection sector has to be a multiple of 3. So let me just say that again. The eta, the ordinary Z2, exchanges these two product states. The D, on the other hand, exchanges the GHZ state with the paramagnet state. And since the non-invertible symmetry acts on the O spin up and the O spin down state in the same way, that means when it acts on the GHZ minus state, which is just the difference between these two, it gives you 0, showing the non-invertible nature of this symmetry. Okay. Any question about this one? And of course, you can find the basis between these states. Just like in the ordinary Z2 symmetry breaking phase, the superselection sectors are in the product state basis. But in finite volume, you should take the sum and the difference, namely the GHZ plus and GHZ minus states that diagonalize the symmetry. Here you have 3 states, so there will be 3 linear combination of these states that diagonalize both the Z2 symmetry and the non-invertible symmetry. Yeah.
You always get ground states that are best representation of the algebra.
Yeah. Yeah. In the infinite volume limit, you get 3 superselection sectors, and those 3 superselection sectors will have to fall into this representation of D and A. Okay, any other question? Okay, so if not, I think it's actually a natural place for me to generalize many of the discussion here on the blackboard to higher dimensions. So let me move on to that discussion. But let me see, how am I going to organize my blackboard? Oh, no, I want to talk about the defect. Sorry, I almost forgot. Okay, so we spend a lot of time talking about the operator that implements the symmetry. And that's an easy way to talk about a symmetry. You have a Hamiltonian lattice model. What do you mean by a symmetry? You have a conserved operator that commutes with the Hamiltonian. That's how we usually think about it. But there's an alternative way to think about the symmetry, which is very natural from the continuum point of view. So let me try to motivate that a little bit. So let's just think about the Z2 symmetry to start with. For the Z2 symmetry, you can think about the operator, which is just eta. That's the product of X. And in the continuum, in the space-time picture, what would you say? You say, this is our space, and this is the time direction. And an operator eta is just an operator you insert at a given time, which acts on your Hilbert space. From the field theory point of view, it's also natural to consider the following object, where instead of putting inserting an operator at a fixed time, you put a defect. It's something located at a fixed point in space and extends in the time direction. From the Hamiltonian lattice model point of view, you might find this a little bit intimidating. Right? How do we think about this object? But in fact, this, at least for the Z2 case, is just a very fancy way to talk about twisted boundary condition. It just means that as you go around the circle, your operator and fields will experience a change as it goes through this blue line. So we can think about it as a boundary condition, or alternatively, you can view it as a modification of the Hamiltonian locally at one point. So this is a powerful way to think about defect in the Hamiltonian lattice model. So for most of the terms, let's take the critical Ising model as an example. For most of the terms, you keep it as is. You don't do anything. But then at one link, which corresponds to here, you put a minus sign. Well, a relative minus. This is one way this is equivalent to imposing a Z2 twisted boundary condition for the system. You just flip one sign of the Ising interaction. So when we talk about symmetry, we not only have to talk about the operator that implements the symmetry on the Hilbert space, you also like to talk about the defect that's associated with it. One reason is because in the continuum, they're kind of the same thing in Euclidean space-time. And furthermore, the fact that there's a defect or a twisted boundary condition associated with the symmetry highlights the fact that this symmetry respects the locality property. You can use this symmetry to define a new boundary condition. And it's important that this defect is only localized in your space. It's not spread out. Okay, so that's the simplest case for the defect eta. And you can ask what's special about this point. There's nothing really special about the point where you put you flip the minus sign. Just as you impose the anti-periodic boundary condition, it doesn't matter if you do it here or a little bit over there. What really matters is that as you go around the circle, you flip the sign a number of times. And the way that's reflected in continuum field theory is that the defect is topological. Moving it around doesn't change the correlation function. That's a very highbrow way of saying it from the field theory point of view. From the Hamiltonian point of view, that corresponds to the statement that there's a local unitary operator for which if you conjugate the Hamiltonian by, you move this location by 1. In this case, it's manifest what that operator is. You just take the Pauli X operator at site number 1. You conjugate this Hamiltonian by that local unitary operator. It takes this plus sign back to the minus sign, which is the same as the rest of the guy, but then you flip the sign of the Z1, Z2 guy. So it's as if the defect is moved by one side by a local unitary operator. that descends from the fact that it confronts the topological defects in the continuum field theory. Okay, so for ordinary symmetry, it's kind of clear how you will go between the operator and the defect. Now, what about the non-invertible operator, the one we were talking about there? Right, so we spent a lot of time talking about the operator D. I gave 2 or 3 different expressions. What's the corresponding defect? I'm not going to give you a derivation of the defect from the operator, but I'm going to justify why they are related. So instead of writing the defect for D, let me write down the defect for D dagger, just for technical reasons. So again, for most of the site, we leave it as is. That's the ordinary Ising model. But then at one site, which again I chose to be between somewhere around L and 1, we put this. So I have, for most of the terms, I have most of the site I have 2 terms. For this particular one, I only have 1. It's a kind of a funny looking terms. It's Z times X. How is this related to D? So in some of the references, it was shown that you can derive the operator from the defect. And that's what ultimately led to the matrix product operator expression. But let me not do that derivation. That would take some time. I just want to do one simple calculation to kind of convince you that this is the defect associated with the operator D. It's a calculation we can do in real time. And before that, let me just say again, similar to the defect for eta, which can be moved around by a local unitary, there's also a local unitary that can move the position of this defect. It's a simple product of the Hadamard gate and the CZ gate. Okay, for this operator to represent any feature of the non-invertible symmetry, we would like it to have some kind of fusion algebra of the form D squared equals 1 plus eta. So let's see how that comes about. To do that, you would like to put 2 defects. So most of the terms still looks the same as before. But then near these 2 defects, I have minus ZLX1. I have another one that's minus Z1X2. And then after that point, it becomes normal again. Okay. So this is the Hamiltonian that represents the insertion of 2 such non-invertible defects. Starting from here, so even though I should say I shouldn't write arrows in the physics discussion, but here I really means I conjugate this Hamiltonian by this simple unitary operator. This is a CZ gate, this is a Hadamard gate, and you will find the following. And this is a calculation you can really do in real time if you know the action of CZ and Hadamard on the polys. The end result is okay. So don't worry about the turn here, don't worry about the turn here. Similarly, don't worry about there. Everything happens in this local region. That really highlights the locality property of the defects. So what did I do? I start with the Hamiltonian with 2 defects. I do a local unitary transformation. This unitary is localized around the insertion of the defects. And I change the form of the Hamiltonian to this. These 2 Hamiltonians are unitarily equivalent. They share the same physics. But the interpretation is very different. Here you have the insertion of 2 non-invertible defects. Here, this X2 looks like the ordinary transverse field Ising term. This looks a little bit weird. But if you look at this Hamiltonian, you see the first qubit only participate in the entire Hamiltonian through this term. There's no x1. So this is a decoupled qubit. And you can just diagonalize it to be plus or minus 1, independent of the rest. So what we found here is that we started with a system with L site. After this local unitary transformation, we have L qubit, but one of the qubits kind of just sitting there doing nothing. And we can diagonalize it to be the +1 eigenvalue or the -1 eigenvalue. And all the dynamics happen for the rest of the L-1 qubit. When you diagonalize this qubit to +1, this is just the transverse field Ising model without any defect, right? Because this is a minus sign, the same as the rest. And you just have the transverse field Ising model on one less qubit, on one less site. L jumps to 2. You skip one site. When it's -1, this whole thing is plus. And that represents the Ising model with a Z2 symmetry defect, but on only L-1 site. So to put this in words, you can say that this local unitary transformation represents the fusion rule, that d dagger times d dagger is 1 plus eta times T inverse. So how do you understand this equation? You can understand this equation as an operator equation that we discussed over there. You can think about d dagger and eta and T, they're just matrices. And you multiply matrices without thinking, this is the answer you find. But here, there's another way to interpret this equation. You can think about the equality as performing a local unitary transformation. These are the defects you insert. The sum means that there's a decoupled qubit, and you diagonalize the decoupled qubit. And the T inverse, you boldly interpret it as having one less qubit. So this is a quick argument that give you evidence why this defect is associated with the non-invertible symmetry. Yeah.
Like the global parity, but set one here is like the local parity of one single thing.
So this eta on the right-hand side becomes the parity for the L-1 system. You forget about the qubit. This qubit doesn't do anything anymore. You just diagonalize it. Yeah. Argo?
Is there a way to do d dagger d with the translation?
You could, but I have to tell you what the defect for D is. And the fact that D dagger and D as operators are related by a lattice translation, the way to think about it as defect is that you have to add an extra qubit, and then that just automatically makes it work. Yes? Very good question. Yeah, but unfortunately, I won't have time to talk about it. So the full answer is that for each of the two systems, H sub eta and H sub D, I have to analyze the symmetries all over again. And you will have a different kind of symmetry algebra. Sometimes the non-invertible symmetry becomes invertible. It takes a lot of work. It's very interesting. I just don't have it. Yes, so. I think so. I don't think I have a proof, but I think that's the expectation. Yeah, and you also have to clarify what we mean by descent, because for the operator, it involves lattice translation. And for the defects, we have to interpret that as adding or deleting qubits. And it can get more subtle when you deal with more subtle symmetries. Yes?
Is it obvious why removing a qubit corresponds to T inverse?
That is more of a matter of choice, because going in this direction versus that direction, there's no difference. But once you make that choice, just like we have to make a choice between D and D dagger. But once you make that choice, you'll find a consistent algebra. Yes?
I interpret this correctly when I say that we have the +1 case which gives the +1 case gives the translation, -1 case gives the eta, and then
Eta times T inverse. So in either case, in either +1 or -1, you have one less qubit. So there's an overall factor of T inverse indicating that one qubit is removed. Yeah. And then it's a relative minus sign, just like in the H sub A. Yes.
Find the Hadamard and CD gate that would shorten your spin chain and therefore
You mean this guy? I don't have a universal answer. Sometimes we just have to play with that to simplify it. Yeah. Another way to put it is that the expression for the defect Hamiltonian is not universal. I choose this particular expression just for convenience, but I can also, on top of that, do any local unitary transformation. For instance, I can even change one of the x to y. So everything should be viewed as up to local unitary equivalence. So it's just that for this particular representative of the defect Hamiltonian, this is the local unitary that does the job. But there's nothing universal about it. Yeah, Yunjing. Yes, yes. In this particular case, it just so happens that the movement operator for the defect turns out to be the same as the fusion operator. But that generally, for other kind of symmetry, might not be the case.
Two defects next to each other by the movement operator.
So sometimes even, so your point is that, if you have two defects very far away, let's move them one by one, and eventually they will collide. Sometimes you might even have to do more after they collide to simplify the expression. As I said, there's nothing universal about it. It depends on your representative for the defects. Everything should be modulo local unit. Okay? I see that I'm running out of time, so I guess I won't talk about the 3+1, or how much time do I have? I'll sketch that in 5 minutes. And look, okay, yeah, even better. So let me give you, so far we talked about 1+1D, but let me say one very simple generalization to 3+1D. And this is based on a paper with Pranay Gorentala and Nat. Since I'm running short of time, I won't write the reference. So the generalization is to 3+1D lattice Z2 gauge theory. I should say that this is Wegner's lattice Z2 gauge theory. And I will soon explain the connection to the toric code. And it's very nice that Caroline set up the framework for 2+1D in the morning, so I can quickly go through this model. So again, I have qubits, but now the space is three-dimensional, but I put the qubits on links of a periodic cubic lattice. Okay? So instead of putting them on site, I put them on links. And what is the Hamiltonian? The Hamiltonian is very similar to the one that Caroline talked about in the morning. And many of you must have studied this many times. So you have a plaquette terms made out of the Z's. And I'm going to add this transverse field term. This is just X on the edge. And there's a Gauss law term. So this term is just this. It's associated with a site, and you put all the X on the site. Okay, so this is the model. For most of our purposes, you can set G to infinity. If you set G to infinity, that's imposing the Gauss law strictly. But the statement also holds true when you set G to be finite, and in that case, you are imposing the Gauss law energetically. In the former case, when the Gauss law is imposed strictly, the Hilbert space is no longer a tensor product Hilbert space. In the latter case, when G is finite, you impose the Gauss law energetically, the Hilbert space is still a tensor product Hilbert space. But the operator I'm going to discuss will not depend on, it acts on both Hilbert spaces. Okay. If you set H to be 0, this is the 3 plus 1D Tori-Code Hamiltonian. And many of you are experts on this model. Notice that I only turn on the deformation for X, but not of Z. I'm not adding linear term in Z. In the absence of this term, you will have a one-form global symmetry and a two-form global symmetry. When the Gauss laws is imposed strictly, both the one-form and the two-form global symmetry are topological. When the Gauss law is not imposed strictly, one of them will be non-topological. Okay. Anyways, I'm only turning on one deformation so that I will have a one-form global symmetry. Now, what is this one-form global symmetry? It's just I'm going to call it eta again. But it's a product of the X, but you take the product of the X only on some two cycles on the dual lattice. Okay. So this is not an operator on the entire span over the entire lattice. It's only on a two cycle in your three-dimensional qubit lattice. To be more precise, the dual of it. Okay, and you can easily check that this is a symmetry that commutes with the Hamiltonian for any choice of the two cycle. Okay. So the phase diagram looks like this. What do I talk about the phase diagram now? So when H over J is very small, you are in the Tori-Code phase. Let me call it the topological Z2 gauge theory. It's a deconfined phase, as some of you will call it. When H over J is very large, you are in the product state phase. And Caroline already talked about a similar phase diagram in 2 plus 1D. In 3 plus 1D for Z2 gauge theory, the only difference is that at the transition point, this H over J equals to 1, this is a first order transition for this particular model. In 2 plus 1 is an Ising star gapless second order transition. So it's a very straightforward generalization of the Ising model in the sense that there is a generalization of the Cramer's one-year transformation. And here's the Wagner transformation. The Wagner transformation maps XL to a product of ZL prime. And where's the product over? The product has to be over some plaquette. And this plaquette is this edge with a half lattice translation. So you should view this relation as the generalization of the one over here. In 1 plus 1D, xj is mapped to zj plus 1. A site variable is mapped to a link. Which link? Is the link that's related to the original site by a half lattice translation. Here you start with an operator on the link. You do this transformation. You map it to a product of z's around a plaquette. Which plaquette? The plaquette that's obtained by the link you started with a half lattice translation in a diagonal direction. And similarly, you map it to you map the product of z to a single x with a half lattice translation. And by this point, it should not come as a surprise that this cannot be implemented by an invertible operator, because if you take the product over the entire periodic cubic lattice, you find 1 on the right-hand side, you'll find something non-trivial on the left-hand side. So it has to be implemented by a non-invertible operator. I won't have time to write down this operator, but the simplest way to present it is to generalize the MPO presentation there. So in this case, it's a PEPO. But in the remaining 2 minutes, let me just comment on 2 features of this PEPO. The most interesting question is, what is D squared? In 1 plus 1D, D squared equals 1 plus eta times T. Great. But there, both D and eta, they spans over the entire Ising chain. Right? So you don't think, you know, these are just operators. So square one, you get the sum of the other two. Great. But here's different. D is a PEPO that spans over the entire cubic lattice. Eta, on the other hand, is a one-form symmetry. It's only supported on the 2 cycles in your 3-dimensional spatial cubic lattice. So how do we write an equation that will make sense? Well, there's only one equation that will make sense, and that turns out to be the correct one. If you don't know where to put your one-form symmetry operator, you simply sum over them. Okay. So you take your cubic lattice and you sum over all 2 cycles in the dual lattice. You have to normalize it by 1 over 2v. V is the total number of sites. And similar to 1 plus 1d, there's going to be a lattice translation in the diagonal directions at the end of the day. Okay. So that's something you can show using the explicit PEPO expression. And the final thing I want to say, which will take only 1 minute, is the analog of those equations. How does it act on the state? And in particular, I can focus on this one. To be more precise, I'm not looking at this model. I have to, again, do a deformation so that the ground states are relatively simple. But let me gloss over those details. This is a first-order transition between the topological Z2 gauge theory and the product state. Let's put the system on a torus. Here you have 1 ground state. Here you will have 8 state. The 8 comes from putting the Z2 gauge theory on a cubic. So here, at this transition point, you will have 1 plus 8 state. The 8 are the toric, come from the toric code. And you can show that this D act in the following way. So when D act on the product state is this ground state over here. Give you 2 times the toric code ground state. And if you act on the toric code ground state, it gives you the product state. So it's a direct generalization of the 1 plus 1D case, where the GHZ plus state is now replaced by the toric code ground state. There was a question? There should be, yeah. No, I was waiting for that question. So the question is, which toric code ground state? I just told you that there are 8. You can ask the same question up there. When you act D on the O plus product state, which on the right-hand side, you are in the older phase. But in the older phase, you have 2 low-lying states. Which one of them? Well, the answer is the GHZ state in 1 plus 1D. So we have to ask what's the analog of the GHZ state for the toric code. The distinguishing feature of the GHZ state is that it's an eigenstate of the Z2 one-form symmetry. And by the same reasoning, here you pick the toric code ground state such that eta has positive eigenvalues for all choices of the 2 cycles. So it's the ground states that diagonalize all the one-form symmetries. And just to make it even more explicit, you can write it as this. You can start with the O plus ground state, and you add all possible loops of Z. So this is the so-called loop gas expression for the torical ground state. Okay, I'm running out of time, so let me just summarize here. In 1 plus 1D, the non-invertible symmetry exchanges the order with the disorder phase. There's a simple generalization to 3 plus 1D, where the non-invertible symmetry exchanges a trivial product state with a non-trivial topological order state. Okay, thank you.
I think we should postpone the question to the other time. So Shu-Heng will also be here next week, so it's
Yeah.
so now we really get it.